Hello and welcome to another lecture where we are going to look at an important physics concept. In this lecture, we are going to look at a situation whereby we are looking at how does the weight of a person who is in a lift change? How does it compare with the actual weight of the person when the lift is not moving? So I'm going to look at different situations. When the lift is moving up and when it is moving down, when the lift is accelerating or decelerating or moving with uniform speed but moving upwards, or when it is accelerating, decelerating, or moving with uniform speed but moving downwards. So I've got about 8-9 different situations that we are going to look at. But before we do that, I'd like us to consider two concepts. So the first concept that I'd like us to understand is that one of normal reaction, or the contact force between two surfaces. For instance, if there is a surface here, there is a surface, there is an object on that surface. One of the forces that this object exerts on the surface vertically downwards is its own weight, given by W, the letter W, and it is related to the mass of the object by this expression here. So if we know the mass of the object, for instance, if the person on the lift has got a mass of 70 kilograms, and we can take the value of the acceleration due to gravity, or the value of the gravitational field strength to be 10 Newton per kilogram, then the weight of this person is 700 Newtons. That is the amount of force that the person exerts downwards on any surface which that person is stepping on. In this case, the person is on the weighing balance. So the person is exerting a force of 700 newtons on the pan of the weighing balance. On the other hand, the surface of that balance is exerting an upward force on the person, and that force will be equal to 700 newtons if the object is stationary. We are going to see that that value of R can change. It is not always equal to the weight of the person, especially when that system is not in equilibrium. If that system is in equilibrium, then the two forces are equal and opposite in direction according to Newton's third law of motion. So I want to refer to this force as the normal reaction. In many situations, we refer to it as the normal reaction, but the actual name of that force is the contact force. Contact force. But for the sake of this video, we are going to refer to it with a common term that students usually use, and that is normal reaction. The second concept that I'd like us to remember in this study is that one of F is equal to ma. This equation stems from Newton's second law. F is the resultant force which acts on an object of mass m, producing an acceleration a on that object. And the direction of the acceleration which is produced by this resultant force is the same as the direction of the resultant force itself. So if we know the direction of the acceleration, we should know that the resultant force is acting in that direction. The converse is also the case, is also true, that if we know the direction of the force, we should know the direction of the acceleration, because the two are always in the same direction. After all, the two are vectors, and because one is producing the other, in this case, the resultant force is the one which produces the acceleration, then the acceleration should be in the direction of the resultant force. The other one is, how do we determine a resultant force on an object which is acted upon by two forces which may be in the same direction, in opposite direction, but they are parallel to each other. That is the kind of situation that we are going to deal with. For instance, if I've got a force P acting in that direction, and I've got a force Q acting in the opposite direction, and when we look at the arrows, P is larger than Q, then the resultant force is to the right. And then how do I get its magnitude? That resultant force, which I'm going to call F, is given by the larger force minus the smaller force. That is always the case. So in this case, I can tell just by looking at the magnitude of the forces that the resultant force is to the right, and therefore this object M will accelerate to the right, like that. Now, let's look at another situation. I've got two forces. There is one which is K, another one is M. Now, by looking at the arrows, I may not be able to tell the direction of the resultant force. But if I've been told that the acceleration is to the left, then what conclusion do I make? I make the conclusion that M must be greater than K, and in order to get this resultant force, which is F, since M is greater than K, how do I know that? The acceleration is to the left, and therefore the resultant force is to the left, which means that M must be greater than K. In fact, that is what I ought to have written here. Made that mistake. F is M minus K. That is how we deal with the concept of the resultant force, how to determine its direction. I can either use acceleration or the actual magnitudes that have been given, and then I substitute those values here. And then I have already looked at the concept of the reaction force. Now let's go to the first situation where the object, the person, is standing on the weighing balance, and the weighing balance is in the lift, but the lift is stationary at the ground floor. And this is the situation I have. The lift is stationary at the ground floor, and the two forces which are acting are the W. Remember, the mass of this person is 70 kg, so his weight is 700 newtons. The reaction is what I want to find out, because the balance reads the reaction. It reads the amount of force that is acting on this person from the floor. That is what the balance reads. So in this case, the acceleration of the lift is 0. Let's use the equation F is equal to ma and see what we get. So resultant force on the person is going to be equal to the mass of the person times the acceleration of that person. Remember, the acceleration is 0. So that means I can just assume that the upward force is greater than the downward force, is equals to m, which is 70 times 0. And you can see this one gives me, to the right, I get 0. So if r minus 700 is equals to 0, it means r is equal to 700 newtons. And this is what the balance reads. So it reads the correct weight of this person. Now let's look at a situation where the lift is accelerating upwards with a certain amount. Like in this case, we are told that the lift is now accelerating upwards with an acceleration of 2 meters per second squared. So I can put an arrow here, actually double arrow. That's how we always represent acceleration. A. Now I can see that the acceleration is upwards. What have we just learned? in this first slide here, we learned that if we know the direction of the acceleration, we can tell which of the two forces acting in opposite directions is greater than the other one. So if the acceleration is to the right, then we conclude P is greater than Q, and in order to get the resultant force, I do P minus Q. And that is the exact situation that we are faced with here. This is a situation. So when it comes to using the equation F is equal to ma, I should know that R is greater than W. W is 700. The mass of that person is 70. Of course, the acceleration is 2. And we're going to say that R minus 700 will be 140. In other words, the resultant force acting on this person now is 140 newtons. And that is the force which produces that acceleration of 2 meters per second squared. Therefore, R, if I add 700 to both sides, I'm going to get 840 newtons. So you can see now the balance is going to give us a weight which is greater than the actual weight of this person. The actual weight of this person is 700 newtons. But when the lift is accelerating upwards, it gives us a reading which is greater than the actual weight of the person. This is what we call the apparent weight of the object. The weight the object appears to have. Apparent weight. The weight the object appears to have. That is not its weight. It only appears to weigh that much. It appears to weigh more than its actual weight. And this is where now I come to that other point that I had mentioned earlier, that R is not always equal to W. This is a mistake many students make. They always assume that the normal reaction is always equal to the weight of the object. That only appears, it will be true if that system is in equilibrium, is in a state of rest, for example, or dynamic equilibrium, like we are going to look at in the next situation when it's moving upwards with constant velocity. And let's go to that one right away. So over here, the object is moving upwards, but its velocity is constant. By mentioning the fact that the velocity is constant, we immediately know that the acceleration must be 0. If the acceleration is 0 and we are using this equation F is equals to ma, this time it does not matter whether we do W minus R or R minus W, but since it is moving upwards, let me just use the same convention and assume because the acceleration is upwards, the upward force R is greater than the downward force, which is the weight, which is 700 newtons, is equals to 70 times 0. And here you're going to see that the value of R will be 700 newtons. You know, it is similar to that situation when the lift was stationary. So there are two situations where the value of R will be equal to the value of W. And this is, number one, when the lift is stationary, or when it is moving upwards with uniform velocity. And we are going to see another situation when it is moving downwards, again with uniform velocity. But let's wait until we get to that point. So here, when it is moving upwards with uniform velocity, let me go back to where I was because it was here. When it is moving upwards with uniform velocity, then the value of R will be equal to its actual weight, and therefore the balance is going to read the actual weight of the person. Let's go to the next situation here, where the lift now decelerates upwards. Decelerates upwards. Before I go to that, I'd like to go to the previous slide here, where we saw that the balance gives us a weight greater than the weight of the person. Let's see what causes this value, or what factors determine the magnitude of R. It is A. If we make A to be bigger, like for example, if I make it to be 3, which means the lift is going to accelerate upwards with a higher magnitude of the acceleration, then it will make this one to be 210. 210 will make the value of R to be 910. So you see that the higher the upward acceleration, the greater will be the value of R, and the greater will be the reading on the balance. That is the reason why when you find that the lift is accelerating upwards, you always have this feeling that the ground is sort of pushing you upwards, and you feel a little bit unstable, especially if you're not used to traveling or to using the lift. You find that the first time you get into it, you can even feel a little bit dizzy, because you find that the ground appears to be pushing you upwards. It's because the lift is accelerating. So you can tell when the lift is accelerating upwards by just detecting whether the ground is pushing you upwards, or if it appears to sort of be leaving you sort of downwards. Again, we are going to discuss that in a different situation altogether. So let's put a few points together. When the lift is accelerating upwards, then the value of the reading depends on the acceleration. When the acceleration has got a higher magnitude, you find that the value of R is going to be higher and higher. Now let's go back to where we were. We were looking at a situation where it is decelerating upwards. What do we mean by a deceleration? A deceleration is just an acceleration, but this acceleration has a negative sign. Let's say it is 2 meters per second squared. Let's assume that is the amount of the deceleration. What does it mean by a deceleration of 2 meters per second squared? It means that the velocity of the object is decreasing by 2 meters per second every second. So if at a particular instant its velocity is something like 20 meters per second, in the next 1 second it will have decreased by 2, and now it will be 18. In the next second it will decrease by 2, and then it will be 16. In the next second it will decrease by 2, and then it will be 14. In each case, you can see I'm subtracting 2 meters per second from the previous velocity, the immediate previous velocity. So that is what a deceleration means, that the velocity of the object is decreasing by a certain magnitude in 1 second. Again, let's look at our equation here, which is F is equal to ma. Remember, I know the direction of the acceleration is upwards. That means R is greater than mg. And this one will be 70 times minus 2. This one will give me minus 140. So if I rearrange by adding 700 to both sides, you'll find that this one will be 560. 560. So you can see that the value of R being 560 newtons means that the balance is going to give the weight of a person which is much less than the actual weight of that person. So the person now appears to weigh much, much less. Again, confirming the concept or the idea that R is not always equal to W. It depends on the state of the system. Where R is equal to W, the state of the system is such that it is in equilibrium. And by stating that it is in equilibrium, one of the conditions that must be fulfilled is that the resultant force must be 0. And that means the upward forces, for example, forces in one direction must be equal to sum of the forces in the opposite direction. In this case, upward forces must be equal to downward forces. And that is the only situation where R is equal to W. So I'd like you to use that situation where you always say R is equal to mg with a lot of understanding. And that is what we are looking at. So here the person weighs less. The person feels lighter. This is again where when the lift is moving upwards, you'll feel as if the ground is leaving you, sort of. Because you become a little bit lighter, you become a little bit dizzy. You may feel a little bit dizzy when you're in the lift. But it's not a cause for concern. It just comes when you're using the lift for the first time. But once you get used to using the lift, that condition usually dissipates. It disappears. So let us look at the next situation. Before we look at the next situation, or what will happen if the deceleration is 10 meters per second squared, meaning that what would happen if the acceleration is minus 10 meters per second squared? You'll find that if I substitute that value here, it will make the right-hand side, the left-hand side remains the same. The left-hand side will be 700, and you can see that will be minus 700. And when I add 700 to both sides, I get the value of R to be 0. This is one of the situations where the person will feel weightless. Your feet will just be in contact with the surface, but this time you won't feel as if the surface is pressing on you. No, you will be weightless. You will be weightless. And you can just imagine what happens if A is now greater than 10. If it is greater than 10, you'll find that R will have a negative value. You see, that is the first situation. Let's look at if A is equals to, like, for example, minus 12 meters per second squared, you'll find that if we substitute these values just the same way like we are doing, we're going to have 700 R minus 700, which will be equal to 70 times 12. And this will give us a value. Of course, there is a negative here because the A has a negative sign. Let me see what that one will give us. It will give us minus 840 newtons, meaning that the value of R, if I add 700 to both sides, the value of R will be minus 140 newtons. What does it mean if R is minus 140 newtons? And let's not lose sight of the fact that, I hope I mentioned this, that when R reads 0, it means that the apparent weight of that object is 0. The reading on the balance will be 0. How about when it is negative? These balances are not calibrated to read negative values of the forces. It will simply read 0, but this is important. If R is negative 140 newtons, the balance will simply indicate that the weight of this person is 0. But if you are physically attached to the floor, like for example, you can just imagine a funny situation where you have, you have been glued to the floor. You will tend to pull the floor upwards. That is what will happen. You'll tend to pull the floor upwards. And if it is calibrated to read negative values, it will read negative 140 newtons. Practically, what has happened here is that you will literally, because we are not glued to the floor of the lift, you will literally leave the floor, like you will fly off the floor. Of course, it will happen just briefly, just very, very briefly. But the accelerations and the decelerations of the lifts hardly go to these extreme values. We are looking at what can happen if this happens. Now let's look at a situation where the lift is now accelerating downwards, and the acceleration it will have is A. Again, I'm using 2 meters per second squared. Now, using the equation F is equal to ma, I can see that in order to get F, I can use the direction of A, which is downwards, and I conclude W must be greater than R. Again, you can see that trick. You can see that trick that I'm using here. I know the direction of the acceleration, so the force which acts in the same direction as the acceleration must be bigger than the force which is acting in the opposite direction. That is the trick that I'm using. And if you get this concept, it will make this kind of problem much, much easier, because you will have understood everything about the apparent weight of an object in a lift which is in motion. So here we have W minus R. Why W minus R? A is in the direction of W, therefore W must be greater than R. Of course, to the right, I'm going to have 70 times 2, which will give me 140. This time, I'm going to have my weight here is, I forgot to indicate it, it's 700 minus R is going to be equal to 140. And when I rearrange, I get, if I bring 140 to this other side, I'll be subtracting it to get 560 newtons. And R moves to the other side. I'm going to have R like that. So if the lift is accelerating downwards, and by acceleration means that the velocity of this object is increasing by 2 meters per second every second. So if the initial velocity was, let's say, 0, in the next 1 second, it will be 2 meters per second. In the next 1 second, it will be 4 meters per second. In the next 1 second, it will be 6 meters per second. You can see I'm adding 2 meters per second, 2 meters per second, 2 meters per second to the previous value to get the new value of the velocity. That is what an acceleration of 2 meters per second or any other acceleration means. Now, since that is the case, the body is going to weigh less. The person will feel as if the ground is leaving their feet. They feel a little bit lighter. Again, that dizzy effect can come in momentarily during the acceleration. Remember, it is during acceleration of the lift that the person usually experiences this dizziness momentarily. Like I said, it's not a serious thing. It's not something to be worried about, but it's something that if you're very keen, you will be able to observe, you'll be able to notice. So let's go to the next section. And before I leave this one, I want to assume, how about if the acceleration of the lift downwards is 10 meters per second squared? What will happen? Let's substitute our values here. My W is 700. This W here minus R is going to be equal to 70 times 10. And you'll be able to see when I rearrange, I'm going to get my value of R to be 0. Again, this person will feel weightless. Your balance will read 0. When the acceleration of the lift downwards is 10 meters per second squared. The other time when he felt weightless was when the deceleration of the lift upwards was 10 meters per second squared. Now, the acceleration of the lift downwards this time is 10 meters per second squared, and he feels weightless. So what are the two situations that the person in the lift will feel weightless? Number one, it is when the lift is moving upwards with a deceleration of 10 meters per second squared or higher. Or when this lift is accelerating downwards with an acceleration equal to the acceleration due to gravity. You can see this acceleration here is equal to g when A is equal to g. Now, if A is greater than g, then the ground, the floor of the lift will literally leave your feet and you'll just be suspended in air this time. Chances are that you will be suspended in air and you will tend to be left behind by the lift because your acceleration is 10 meters per second squared. It is free fall. Your acceleration is equal to the acceleration due to gravity. But the surface on which your feet are resting is moving with an acceleration greater than the acceleration due to gravity. So the two bodies are moving with different accelerations. The lift in which you are is moving with a higher acceleration downwards than the acceleration which you would normally have when you're falling freely. So you'll sort of be left behind. Of course, this one is a funny situation because you will be left behind and you will find that with the time, your head will be in contact with the roof of the ceiling, with the roof of that cabin, with the roof of the lift. It is your head now which will be in contact with it like this. It's a very funny situation. But it's good to imagine of these situations, especially when we are looking at objects which have got engines and the accelerations which these objects have may be higher than the value of the acceleration due to gravity. So you may find it uncomfortable with your head being in contact with the ceiling. So chances are that you may end up turning around because you may have that impression that actually the ceiling is like the floor. You may have that kind of feeling. But this one is driving this discussion to the extremes. But it's always good to imagine such situations in order to understand this area very, very well. So let's put a few points together. When the acceleration of the lift is equal to 10 meters per second squared and it is accelerating downwards, and 10 meters per second squared is equal to the acceleration due to gravity, the object will be weightless. Let's look at another situation where it is descending at uniform velocity. Of course, this is when now it is descending with uniform velocity, so the acceleration must be 0. If the acceleration is 0, when we use F is equal to ma, you find that F will be, because the acceleration is downwards, I'm going to assume W, which is 700, minus R is equals to 70 times 0, and we find that our R will be 700 newtons. So this is the third situation where the weight of the object is equal to the real weight it has when the lift is stationary. Remember, when the lift is stationary, we say that is the first situation when R is equals to W. The second situation when R is equals to W is when the lift is moving upwards with uniform velocity. And the third situation is when the lift is moving downwards with uniform velocity. So you may be asked a question like this. What three situations does the balance give the actual weight of the person? Mention three situations that the balance reads the actual weight of the person. The first situation is when the lift is stationary. The second situation is when it is moving upwards with uniform velocity. And the third situation is when it is moving downwards with uniform velocity. So uniform velocity, or an object being stationary, shows that R is equals to W, and these are states of equilibrium. The first one, when the lift is stationary, is referred to as static equilibrium. The object is not in motion, it is stationary. So the kind of equilibrium where in that situation is static. The second two situations whereby the object is moving but it appears to be in equilibrium is referred to as dynamic equilibrium. So for a system to be in equilibrium, it does not necessarily mean that it has to be stationary. It can be in motion, but the velocity has to be uniform for the acceleration to be zero. In fact, for you to be on the safer side, when you are looking at equilibrium and you are dealing with the resultant forces, always resolve those forces and then use F is equal to ma all the time. You can never go wrong. Let's look at the last situation where the lift now decelerates downwards. What does it mean when it decelerates downwards? Remember the meaning of deceleration. When an object decelerates, its acceleration is negative. And I've already explained what it means by a negative acceleration. It means that the velocity of the object is decreasing by a certain amount every second. All right, when we use F is equal to ma, as is the tradition, you can see that in all these situations I'm using F is equals to ma, a very important equation. And that is why I started with it. I asked you to be able to understand what F is equals to ma means. This is the resultant force, which produces an acceleration A on an object of mass m on which it is acting. The direction of the acceleration is the same as the direction of the resultant force. So if you know the direction of the resultant force, you automatically will know the direction of the acceleration. Or if you know the direction of the acceleration, you already know the direction of the resultant force. Where is that important? It helps you to know, is the resultant force P minus Q or is it Q minus P? I don't mind repeating this because understanding of this concept is what ensures that you understand this situation and many other situations where you use Newton's second law of motion. F is equal to ma. I don't mind repeating it. It's so important. If the acceleration is in this direction, you conclude F must be greater than Q and the resultant force, this one, must be P minus Q. On the other side, if the acceleration is in this direction, then you conclude m is greater than k, and therefore the resultant force is m minus k, which is equals to ma. Like that. So let's go to that last situation. In order to get this F, I know the direction of the acceleration. Remember, it does not matter whether it has a negative sign or a positive sign. So long as it is A, I know it is accelerating in that direction. Let other things work out all by themselves. Just follow the rules. I know the direction of A. So between R and W, which is bigger, it is W. So I write 700 newtons, which is W, minus R will be equal to 70 times minus 2. This will give me minus 140. When I rearrange, I find that my R is this R will come to this other side, and this one will go to the other side. I'll have to add, I'll get 840 newtons. So when the lift is decelerating downwards, the lift will give a higher reading of the weight of this person. In this case, you will find it's as if the ground, the floor of the lift is pressing upwards on you. Of course, you can see that this force can be very big depending on the A. If the A is very, very big, then you find this force can be very, very big. And that is how you deal with this situation where we were looking at the apparent weight of a person in a lift which is in different situations. I've looked at 9 situations in total. Replay this video. As a matter of fact, if you look at the timestamp, if you hover your cursor on the scroll bar or at the timestamp, you'll be able to see each one of these situations. I have numbered them starting from number 1 all the way to the last one, which is this one. So if there is any one of them that you'd like to review very, very fast, hover the cursor on the scroll bar and you'll see numbers pop up. Those numbers which pop up have got simple headings, and those headings are the way I have written them down here. So just click on it and the video goes to that section and you repeat that particular section. I hope this video has been of much help to you. If this is your first time to be on this channel, consider subscribing, because that will be important to this channel. And at the same time, give this video a thumb up. Just click on that symbol that shows a thumb up, and you can even share this video with your friends. This helps this channel in several ways. It helps the algorithm of YouTube to understand that this video is important and people are sharing it. So if you're interested to see my channel grow, just give the video a thumb up and share it with your friends. Otherwise, I'll see you next time when I share with you understanding another concept in physics. Bye-bye.